Most of you have heard this term in several times in during your studies or during your research purpose. So what does this survival analysis means, and why do we need this sort of analysis for that specific type of data? So that is what we will be discussing on today's topic. So today's topic will be to provide an introduction to survival analysis and to see what is the most common method to which we use in survival analysis, like Kaplan-Meier survival time estimates. So the testing of survival analysis and Cox proportional hazard model we will be discussing on the next session. Okay, so we will move on to survival analysis. Okay, I hope you can see my screen, right?
Yes, yes, we can see. Yeah.
Okay, so before we move on to survival analysis, we have to define a time to event data. In simple term, a data of time elapsed before a certain event experienced is called a time to event data. Why this is relevant is because we have two informations there. So we have the duration which elapsed by a certain subject, and we have to know whether that specific subject experienced a certain type of event or not. So this is something which is happening in a longitudinal manner, uh, unlike any other variable which we have defined before, even though and even like dichotomous variable like yes or no, or a continuous variable like height or weight. This is something different. This actually falls a separate category, like time to event data. It has been defined as a time to event data, which enclose the information of the duration which was elapsed, and whether that certain event happened or not during that specific duration. So why we use time to event data? To see how long something will survive. So it may not be our interest may not be always on death. It can be relapse, it can be a lifespan of a light bulb, or it can be a lifespan of a specific type of instrument or electronics. So in all the cases, the data will be the same. Like it will be a time to certain event data. Time to failure need not be failure. It can be a time to success also, like time to certain event. That is what it means. To investigate the factors influencing the time to event. So this is one other aspects of measuring the time to event data. What all are the factors which can cause, or which can increase or decrease the duration for a certain event. So for those type of analysis also we will use time to event data. To compare the duration elapsed between groups, so we have two groups, or we have a light bulb of two different companies. So which one will be better? So whether that the difference we are seeing is significantly, whether the difference we are seeing is completely occurring due to randomness, or whether there is any significant association between significant difference between these two groups. So time to event data are mainly used for these three type of analysis. Why do we need a different analysis? Why not compare the proportion of events in your group using a risk or odds ratio or logistic regression? So when we compare simply the events, or a specific type of occurrence of certain disease or certain relapse or something like that, why don't we do it using risk or odds ratios, or any kind of proportions and frequency measurements we have learned in the previous classes? The problem is it completely ignored the duration factor uh, of that specific process. So if we are not interested in that duration factor, we are always free to do risk ratio or odds ratio, or any sort of descriptive frequency table, and compare it via that. So but when we do a time to event analysis, we are same time wanted to analyze the occurrence of that event and the duration of that specific event will happen. So that's why, so the proportions will ignore the time. And why not compare the mean time to event between groups using t-test or linear regression or any sort of generalized linear models, which we have discussed in the previous classes. So what will happen is it will ignore the censoring. So what is the censoring? We will move on to the next slide to see what is censoring. So uh, okay, I'll just take that slide and go back to the previous slide. There was some sort of issue with the presentation. Like, yeah. So censoring of data means subjects are said to be censored if they are lost to follow up or drop out from the study, or if their study ends before they die or have an outcome of interest. So basically, censoring means we are following that subject, but we don't know at what time the event was happened. So censoring is basically with associated with the specific event. So we don't know whether the event happened or not, or sometimes if it is left censoring, then we know left censoring or intermediate censoring, we know that the event has happened, but we don't know exactly what time it was happened. So for example, they are counted as live or disease free for the time we enrolled in the study. So that's the way we use. So there is some sort of unknown in the event factor, but not on the time factor. Is to be cautious. Like if the time is unknown, then we will not include the subject for the analysis. But if the event is unknown, we can still include that duration of that specific subject in the analysis. So that is what we are missing when we are comparing with the t-test or linear regression or any kind of continuous measurement analysis. So what is survival time? This cartoon say your expected lifetime left is 31 years. Expectation can have an error of plus or minus 30 years. So basically it can be next year to next 60 years. So this is just a cartoon. So just to see what the survival time means. So the time starting from a defined point of occurrence of a given event, starting from a defined point to the occurrence of a given event. So we should be very cautious about defining the point, starting point to the occurrence, defining the starting point. In normal cases, there are two ways to do that. Suppose we are doing some sort of clinical trial or some sort of research. Sometimes we take the time to certain event as the time of recruitment for that subject or time of randomization of that subject as a starting time, and follow them up for the next 5 years, 10 years, 3 years. It depends on what will be our event of interest. But yeah, the starting time will be usually the date of randomization or date of inclusion to the study. But sometimes we should be very cautious because the starting time can be the time of completeness of a certain procedure. If we are doing certain some sort of analysis, like if we are looking for uh, duration of survival or duration of disease-free survival after an implant in the heart. So the start time will be the specific time of implantation of that specific device into the heart, or any sort of procedure to a patient. So it is very important to define the starting point of that time in the survival analysis. The event should be well realistic and well defined. What it means is like, suppose we did an analysis like whether the patient die or not, and the patient was expected to live for another 10-15 years, and we are conducting a study whether the patient die or not is actually completely foolishness. So so that is what it means by realistic. So we should actually expect a realistic event which will happen in the duration of our study. For example, in case of cancer research, it can be a relapse. So relapse will usually happen within within 5 years for most of the old age cases. So we need not go for the death, but we will go for the relapse as an event. So definition of event, we should be very careful, because it need to be realistic and should happen within our study time period. And it can go on the other way also, like if we have patients dying very soon or patients having relapse very soon, then we can actually, instead of calculating 10-year or 5-year survival, we can go for 3-year, 2.5-year survival rates uh, for that specific type of study. So the event should be realistic and well defined. That is one thing which we need to be very careful. Certain event may occur multiple times during the follow-up. For example, in the relapse case, or the heart attack, a patient can experience heart attack multiple times in his lifetime. So we should be well defined what type, what is our actual event, like time to next heart attack or time to first heart attack, or so when we conduct a study, we should be well defined about uh, which occurrence of that specific event is of our primary interest. We can have multiple secondary objective, but primary objective should be well defined in terms of events. The starting time is very important and should be well defined. As I told you in the first point, in survival analysis, it is very important to define the starting time of time to event data sets. So just come back to the censoring. As I told you, censoring is the unknowingness, or we don't know whether a certain event is happened or not, or we don't know the exact time specifically when that certain event happened or not. So there are three types of censoring. One is left censoring, another one is right censoring, and another one is intermediate censoring. So left censoring means the event was actually happened in the past. This is happening, this type of left censoring most commonly occur for events which will happen multiple times for a specific patient or specific subject. Um, just like heart attack. So from your experience, you may know that a patient may come to your room like having a second or third heart attack, which the first one or the second one in between one, he might not be aware of, like there was a heart attack happened to him, but from the evaluation you might be able to say that there was one incidence for that patient, or two incidents for that patient, or multiple incidents. I'm not sure about what we do, but that is the idea which is meant by left censoring. We know the event was happened before, but we don't know when it was happened. Right censoring means it can be a loose follow-up. We are following up a certain patient, and he decided to withdraw from the study, or he is not responding to our inquiries, whether he experienced that event or not. So it can be a lost follow-up, or in other words, it can be the end of duration of our study. So we decided to follow up patients for 5 years, and he did not experience, or he or she did not experience the event till the end of 5 years. So which means that we don't know whether that patient will have an event or not, because our agreement was to follow them up for 5 years. So that is what we call right censoring. And there can be intermediate censoring. So we know that the patient was not having the event, but after a certain time we know that the patient experienced the event during the follow-up, but nobody knows exactly what time he experienced that event. So that is what we called what we mean by intermediate censoring. So most common censoring what occur is the right censoring. So we will be mostly discussing on the right censoring part, not on the left censoring or intermediate censoring. Another important concept in the survival analysis is the hazard function. The hazard function is also known as the failure rate or hazard rate or force of mortality, not specifically mortality. It can be force of any specific event. And statistically speaking, it is a ratio of probability density function to the survival function, but ignore that statistical part. Just for your reference, I just put it here. But it means a force of occurrence of certain event. I'll give you a best example. Like some of you might have heard about the bathtub curve. So bathtub curve is related to the mortality of an individual. So when the individual was infant or in the early childhood period, the probability of mortality is very high. So infant, so it takes a value very high, and it go down and will be constant in its adolescence or adulthood. There will be some sort of mortality, but it will be very less, and it will keep increasing after a certain age, like 50 years or 60 years. So that force of occurrence is called the hazard function. So we have seen what is the survival time, how we are defining the survival events, or what all are the factors which influencing the duration of influencing the definition of survival time and event. Now we will move on to a very common and very familiar methodology from Kaplan-Meier. uh, they have estimated the survival time using product limit estimate of survival time. So Kaplan-Meier survival estimate is a non-parametric estimation of survival function. So a survival function means what is the probability of a certain individual will be surviving past that specific time point. So what is special about Kaplan-Meier survivability estimate? It is taking into account of censoring, like we have discussed previously. Kaplan-Meier survival estimate is simply the empirical probability of surviving past a certain time in the sample, taking into account of censoring. And it is commonly used to describe the survivorship of a study population, and commonly used to compare the study population using log rank test that we will be discussing on our next session. And it is a very intuitive graphical representation. So on the right side of my presentation, I have represented a Kaplan-Meier survival curve with its corresponding confidence limits at each individual point. So yeah, so this is how it looks like when we plot a survival uh, estimate using Kaplan-Meier method. Um, yeah, I will in the next sessions I will describe how we will interpret the Kaplan-Meier survival curve, which is actually very important. You might have seen this sort of curves in different research articles, which you may have read before. Okay, so we will just see how we are going to, in real life, how we are going to develop a Kaplan-Meier survival estimate using 5 subjects. We have subject A, B, C, D, and E, and we included all the subjects at the at a specific time point for the sake of uh, interpreting this Kaplan-Meier survival curve. I'm very much sure that this is not the real world scenario, but we will assume that everybody starts our follow-up from that specific time point. So there is 5 subjects, and subject E dies after 4 months of follow-up. Subject A actually lost follow-up in 6 months. Subject C dies in 7 months. Subject B and D survived till the end of the study. So we have 2 people, we have total 3 individuals whom we have censored data, which are subject A, B, and D. We are not sure whether those people have experienced that event during our study period or not, because 2 of them actually cross our study period, and one of them was lost follow up during our study period. And we have two of them followed up for a certain time, one for 4 months, another one for 7 months. So how we will be estimating the Kaplan-Meier curve? Uh, just a second. Sorry for the interruption. Okay, so I'll tell you how we will be estimating this Kaplan-Meier survivalship function. So at the beginning, we all will have 100% probability of survival from the starting, because we already are having participating in the study, so everybody should be free of our event. So the first person dies in 4 months. So till 4 months, everybody was alive. So till 4 months, the survivalship function was 100%. So when the first person dies, the survivalship function actually drops, and it takes the value 4/5. So there is one step drop in that survivalship function. And we have one censoring event happen between the next event. So we will not be changing the survivalship function when censoring event is happening, but we will account for that censoring event when we calculate the survivalship function for the next occurrence of that event. So the second event happened at 7 months from our previous example, and we did not see, oh sorry, we did not see any event till the end of our study. So the product limit estimate of survival is surviving interval 1 at risk up to failure, 1 multiplied by surviving to the interval 2 at divided by the risk up to failure 2, which is actually in the first case 4/5 times 2/3, because we have lost follow-up for one patient. So this is actually ending up with 0.533 as a survivorship function. The probability of surviving in the entire year, taking into account of censoring, is actually 53%, just like we have seen before. And we should be very careful. Like it is not 40%, because which is approximately 2/5, because only 2 people survived, even 5 people were included. But it is slightly higher than that, because we don't know what happened with that lost follow-up patient. And it is less than 60%, because if we count only the number of event happened, it was actually 2. So non-events are 3, though it is 3/5. But since we don't know what happened for that specific censored patient, right censored patient during our study, it is slightly lesser than 60% also. So that's the beauty of survival analysis when it comes to product limit estimation. So we know that this function is more than 40 and this function is less than 60. So the best estimate we can have is the Kaplan-Meier estimate, which is actually 53%. So how we could interpret a Kaplan-Meier survival curve. So I just plot a Kaplan-Meier survival curve for our reference, and I will tell you different interpreting scenarios of that survival curve. I'll just, let me take this pen. Uh, can you see I'm drawing?
Yes.
Okay. So as I told you before, everybody starts their event with 100%. So at the beginning of our study, everybody has 100% survival. And at different time points, different individual lost their experience that event, that whenever that individual experiences that event, the survival curve drops step by step. And this horizontal lines within the survival curve, or sometimes it is represented by star, sometimes by triangle, but anything coming in between this survival straight line is called censoring. So we don't know what happened to this patient after this certain time point, but it will not affect the actual survivalship probability till the next event happened. But when the next event is happening, it is counting, it is actually reducing the count by removing this specific subject from the calculation. But till here, he was actually completely a valid option. So as we see here, so usually when we interpret the survivalship function, we take the median survival time. So it is coming around, I think I represented this as years. If it is years, it is coming around 4 point some certain years as a for example 4.3 or 4.3 years for this survivalship function. Sorry for the interruption. Yeah, so this is how we estimate the median survival time from a survivalship curve. Another thing which we should be careful about is the dipping of the curve. So when you see at the initial point, the dipping length was very small, like only this much. But when it comes to the end, the dipping length slightly increases. Or if we have a huge lost follow-up or huge number of not only lost follow-up, most of the time it is like people are still not completing their duration of time, then we will see a very high jumping from in our survival function. This is what it means is like we have a very low sample size or very low follow-up duration from that specific point. For a simple example, if 100 people were started the study and only 5 people were there at four, past the 4 years, even one death after 4 years will drop the survivalship function up to 1 by 5, so, which is approximately equal to 0.2 jump. When one drop here drops the function only up to 0.01, which is actually 1% around. So this drop always will be increasing towards the right side, and huge drops towards the right side means you may not be having enough follow-up for doing any sort of analysis or any sort of interpretation for that specific result, or you are choosing a survival duration which is very high compared to the occurrence of that event. So it can be of multiple reasons, but it generally means that we are not having enough subject during that follow-up duration. So this is pretty much about the Kaplan-Meier survival curve and interpretation. And now we will move on to see how we'll be doing an analysis using this survivalship function, or how we can generate this curve in SPSS. So I'll be just stop my screen sharing and come back after uploading the data. Okay, so now I have uploaded the data, uploaded our data. Basically, I have created this multiple variables just to get you an idea on our next session. So these variables are not much useful to represent our current session like group, age, and gender. But this is actually a data, a random data which is generated by myself. So it has two things like whether the patient died or not, and a duration to death or duration to loss to follow up. So the data looks like this. So 0 represents the patient is alive, and 1 represents the patient is dead. We followed up the patient for 5 years. So basically the maximum of our time is 5 years. So another just to let you know, another confusion when most of analysis, most of the time when we do the analysis, another confusion is that uh, what is the relevance of fixing this upper bound for the survival analysis. This is just to let you know that we always need to fix an upper bound for the survival analysis. Maybe we have followed up for some random 1 or 2 patients for 6 years or 8 years, but our actual study was only for 5 years, and we have followed up most of the patient for 5 years, but 2 or 3 of them were recruited very initial stage of the study and followed up for 8 years or 10 years. We should put those patients, even though we know that the patient experienced that event at a certain time point, after 5 years, we forcefully say that the patient was censored at end of our study instead of putting that specific event up to 8 years, because when we calculate this survivorship function, the software tend to go till the maximum time. So just to avoid that, we put that patient to be censored at 5 years. I'm saying this because this specific patient might have died in 6 year, but I'm saying that I followed up that patient for 5 years and put 0, like he was alive till 5 years. These patients are actually the one who lost follow-up in between. So this patient was followed up for approximately 4 years, and he lost his follow-up at the lost of follow-up. He was actually alive. So that's why his number is 3.99. So this is
Excuse me, sir. I
yeah,
have a question. I have a question here. Can I ask, please?
yeah,
Uh, Suppose we are doing a study which is partly retrospective and partly prospective. For
yeah.
example, we are having a study on thyroid cancer patients, and retrospectively we had 1 year patients, and then again
Mm,
for prospectively for 2 years. So
yeah.
in that case, for the first year patient, the time for which we observe the patient is maybe 3 years, and for second year it is only 2 years, and the last one is only 1 year. So how to, in these cases, how to fix an upper limit for that?
um I'm not sure whether I could completely digest your question, but what I understand is like you wanted to do a study, and for some patients, that you know their history for retrospectively for 1 year.
No,
Is this what?
actually, sir, the example which you are giving is that at a point of time we have started a study,
Yeah,
and then for 5 years we have done that study and follow up the patient for 5 years, and then we have seen that what the status have been.
yeah,
So my question is, if there is a study which is partly retrospective and partly prospective,
yeah. So in that retrospective factor, what is the earliest date you can get information of that patient?
suppose it is 2021. Today I am starting a study, but it is
Uh,
enrolling the known patients of cancers of 2020 also.
so it
And
doesn't matter, like even you are enrolling the patients from 2020, and they are still the history of that patient from 2020. They are having they have that specific type of disease. We can start the follow-up from 2020 as the start date. and we can move forward. If you see in a broader aspect, we will be doing this analysis after 5 years. So the earliest date of that history would be our starting date of that patient. Do you
Okay.
understand what I'm saying? So for this type of analysis, suppose your sample size, your minimum required sample size is 100 patients,
Hmm.
and you got 20 patients who were actually recruited. You know that those were they were having specific type of disease, like in your case cancer, in 20, somewhere around in between 2019 or 2018 till 2021. So you
Hmm.
included those patients, and you have these dates, like they one of them had first visited the clinic with the thyroid cancer on 2018, and to end up the follow-up for that specific patient itself, it will take 2013. So at 2023, at 2023 he will complete his 5 year of follow-up.
Hmm.
But the patient now we are recruiting 2021 will complete their 5 year follow-up in 2016. So basically, we will be analyzing the data beyond some time on 2016.
Hmm. Yes,
So,
sir.
so in that case, what we need to do, what we should be careful to do is, like, we should put this specific 2018 patient beyond, while analysis, not on the database. In the database, you can have the raw data, but when we are doing the analysis or we are estimating the 5 year survival, we should put that patient at 2013 if he is still alive as a censored patient for 5 years. So this is what we need to be careful, because we have a chance to follow them up till 2016, sorry, 2026.
Hmm.
But
Yes.
still, but but still, we, for the analysis purpose, we will put that patient's last follow-up is 2023. He completed his follow-up and he is still alive, and he might have died in between, like 2023 to 2026, but it doesn't matter when we are estimating the 5 year survival.
Sir, if we keep the survival time, means analysis time lesser than 5 years, suppose it is we are able to observe the patient only for 2 years or 3 years,
Hmm.
uh, would still we use the Kaplan-Meier's curve for that?
Yeah, we can still use the Kaplan-Meier curve, but what would be your event is important. So if it is death, I don't think any type of survival analysis will work for you, because most of your patient will not experience the event. So
Suppose it
that,
is recurrence, sir, recurrence for
yeah.
cancer.
So if
In
it
that
is
case,
recurrence, if it is recurrence, it is actually valid. Like usually it takes 18 months. I think 18 months to 3 years
yeah.
to see a recurrence. Yeah. So in recurrence terms, it actually is very valid. And nowadays, what in the higher research, what they do is, like, we till now, in our research, we know that recurrence is highly associated with the mortality.
Hmm.
So we need not always wait for the patient to be mortal.
Hmm.
So if the patient is having a recurrence, he is highly likely to die.
Hmm.
So we take recurrence as the event, and we can get some quick publications where with a good analysis, like within 2 year or 3 year of time span, instead
Okay,
of
sir.
doing 5 year, 10 year, or 15 year study, because that patient, we know that that patient will die very quickly compared to the other patients. But we can stringent our duration of study to 1 or 2 years if we calculate the recurrence as a response event in the beginning of our study. So this is a practice which is very recently in use, and especially it is used in acute leukemia type of patients, because most of the leukemia patients, I mean, most of them, if uh, they are not I mean, most of them will not completely recover, but they do live they will be alive for a long period of time, compared to their relapse. So if they are getting relapse, it will be very quick, like just like I told you, within
Okay,
1 year
sir.
or 2 year. But after relapse, there is a higher chance of death. So why should we wait for death to be an outcome? We can actually put relapse as an outcome. We can reduce that time and check the effect of a specific treatment or anything like that. So if the patient is not having relapse, it means that he is highly unlikely to experience death in the quicker time point. So there is a trend of doing such type of analysis recently. So this is completely a valid option to do. Yeah.
Okay.
Any
Thank
other
you, sir.
any other
No,
question?
no, sir. Thank you so much.
No problem. So yeah, so let's see how we will plot this Kaplan-Meier curve using in SPSS. So as I told you, forget about these three variables. This we will be discussing our next session. So go to analyze. Where is it? Survival, Kaplan-Meier. So in SPSS, we need to define the time and the status variable. So the time is actually a time variable. Just to be careful, this time needs to be defined in scale, not on nominal or ordinal. And death needs to be defined in nominal or ordinal, or we can define it in scale, but usually we'll do it in nominal scale. Yeah. And after putting the death variable, we need to define the event. So if we have multiple values, so for example, I'm not sure how to do a competing risk assessment here, but we may have multiple just like the example you have said for in cancer patients, acute, for example, the AML patients. There is two type of relapse happening. One is molecular relapse, and another one is hematological relapse, I think. So there is two type of relapse. One is actually the some analysis will consider these two of them as a relapse. Some analysis will consider only the hematological relapse as actually the actual relapse. So we can actually specify multiple values here or range of values here, but in our scenario we will specifying one as the event of our analysis. So we have defined our survival time, we have defined our survival event. So let's just check. And we will, by default, we will be having the survival table and mean and median survivals. We can add the quartiles also, but we should have a survival plot. And if we are interested to do the hazard or log survival, we can include that. And if 1 minus survival means sometimes the plotting will be, okay, I'll plot that and show you. So it's actually both of them are the same plot, but one is actually coming from 100% to 0%. Another one is going up from 0% to 100%. So you will understand when you see them. So we will define this one, and we are not doing any testing like factor or strata or anything like that. So, and after that, we'll just press OK. So we know that the total number of patients is 100, a number of events is 50, and a number of censored is actually 50%. So 50 of them experience event, 50 of them not experience event, but all these 50 was not completed the 5-year follow-up. Some of them we have lost follow-up in between. So at time 0, the survival was 1, but the first event was happened from time 0.97. So it was very quick. This is just a random data, so don't try to correlate it with any of these indices or anything like that. So this is just a random data generated, so it may not make any sense when in the perspective of if we compare it with the disease or not. So these are the specific points in the survival time till 5 years. And if we see the cumulative proportion at time, we know that 38% of people have survived till the end of 5 years. So displaying this table is actually foolishness. So Kaplan-Meier curve estimate is actually very common and very accepted, widely accepted way of representation of survival time. So this is how the survival function actually moves on to the 0.38. So the last point at 5 years is actually 0.38, which actually means 38% of the individuals survived till 5 years with that disease. So in if you see here, just like I told you before, here the gems are very shallow, and when you move on here, individual gems are actually really larger than the gems you see here. Since the survival is actually 38%, you may not be able to see a huge difference here, but if everybody was experience that event by the end of 5 years, you might have seen a very large jump, or very few people has been in the follow-up for 4 to 5 years, you might have seen very large jumps in the survival function. So this is actually the rate of incidence functions. This is actually perfectly the reciprocal of this graph. So if you turn this around and put or take a mirror image of that graph, is actually this graph. So it actually gives you the incidence of that the occurrence of that specific event throughout 5 years. So initially no event was occurred, and by the end of 5 years, so around 72 or 62% of the individuals have experienced 62% of the individuals have experienced that specific event. So this is how we interpret, or this is how we develop the survivalship function, and this is actually the survivalship function estimates, like the median, the median survival time. Usually the survival time is represented by median. The median survival time is 4.343, so which means that half of the patients will survive past 4 years, and with a standard error of 0.27, with a lower bound and upper bound of these values. And these are the percentiles. So 50th percentile is equivalent to median, and 75th percentile is actually the the first 25%. 75% of people will survive past 2 years or 2.5 years. So yeah, so we will wind up this session with this survival plotting of the survivalship function, and in the next session we will see how we are comparing two groups of survival with a grouping variable like treatment A and B, how this survivalship function is differing, and how we are going to analyze whether the difference is statistically significant or not. Yeah. Hello. Yeah, there was some noise. I was thinking that somebody's asking something. Okay. Okay, so that's pretty much it about today's session. So any questions?
Thank you, sir.
No problem. So if there is no question, I'll just stop sharing, and yeah.